In a rare alignment, a moon 400 times smaller than the Sun can position itself to perfectly obscure the light of its parent star. This sketch shows how we usually visualize this event. We tend to imagine the Sun, Moon, and Earth clustered together in a straight line, existing at roughly similar scales. But the actual physics are far more extreme. The Sun's diameter is roughly 400 times wider than the Moon's, but it sits 390 times further away. These two ratios nearly cancel each other out, making both bodies appear almost identical in our sky. Since this effect is the result of specific proportions, we can use symbolic geometry on a 2D screen to map exactly how these shadows form. In this GeoGebra workspace, we reduce the celestial bodies to simple colored circles on a horizontal axis. We set their proportional radii using the top sliders, the Sun to 4 units, Earth to 2, and the Moon 2.5. While the distances are compressed to fit on a computer screen, the geometric rules governing the light and shadows remain mathematically accurate to the real world. By simplifying these massive distances into symbolic radii, we can plot the path of light rays. We've isolated a single point of light on the Sun's edge, point P, tracing 2 orange lines toward Earth. These tangent lines rest exactly on the Moon's edges, defining the shadow boundary for this specific ray to show where light is blocked from reaching Earth. A horizontal line connecting the centers to point C, where tangents meet, and vertical radii create 2 similar right triangles. If the Moon's radius is 1, the Sun's is 4, and the Moon's distance is x, what is the Sun's distance? The answer is 4x. A solar eclipse is a predictable geometric event, governed by the fixed ratios of these similar triangles. However, the Sun isn't a single point. It's a sphere emitting light from its entire surface. When we add a second point of light at the bottom edge, point Q, its pink tangent lines cast a shadow at a completely different angle. Animating that point of light around the Sun's entire circumference traces tangent lines for every ray hitting the Moon. Looking past this chaotic web of lines, a single dense region forms between the Moon and Earth where no light rays penetrate. By tracking the behavior of infinite light rays, the visual noise resolves into a geometric void where the shadows overlap. This sharp, dark inner cone is the umbra. This is the zone of total darkness, where every single shadow we traced overlaps. The wider, lighter areas on the sides are the penumbra. In these zones, some light rays are blocked, but others still reach the surface. This map corresponds directly to our experience on the ground. If you are standing inside the tip of that umbra, you look up and see the white corona of a total solar eclipse. Because these are strict proportional triangles, distance is everything. If the Moon's orbit drifts slightly further away, the tip of the umbra fails to reach Earth, creating the rim of fire seen in an annular eclipse. This celestial event is defined by the interaction between massive physical ratios and the clean geometry of these nested right triangles. The path of totality across the Earth follows the same predictable rules of proportion that we find in a simple classroom sketch.